Our universe. I'm Alex McCollin, and you're watching Astrum. Join me today as we learn about the secrets of gargantuan gravitational waves and the ingenious new method astronomers have used to detect them. In a previous episode, we covered the LIGO detector and how it uses lasers to precisely measure the minuscule changes in the length of a tunnel caused by gravitational waves passing through. These gravitational waves stretch and squish space-time, causing changes in the time it takes for light to travel from one end of the tunnel to the other. But detectors like LIGO are only sensitive to a specific kind of gravitational waves. Like light waves and sound waves, gravitational waves can come in different frequencies. And LIGO is only able to listen in to one part of this spectrum, the high frequencies. That's when these binaries are spiraling in on each other rapidly, completing hundreds of rotations per second before colliding in a great bang. But that is also why LIGO cannot listen in on the much earlier stages of these binaries when the objects are orbiting each other at a much greater distance. Because these orbits are much slower, the gravitational waves they produce are of a lower frequency and energy. So you could say, rather than a great bang, they give off a faint hum, combining into one collective signal. Bigger black holes give greater contributions to this signal. The loudest contributors would consist of pairs of supermassive black holes, the kind you'd find at the center of galaxies. These binaries, which consist of black holes billions of times the mass of our Sun, are expected to be rare because they only form when something truly spectacular happens. The merger of two galaxies. When galaxies merge, because of the vast amounts of empty interstellar space in them, they mostly phase through each other. Very few, if any, actual collisions of stars or planets happen. But the stars gravitationally attract one another and merge into one collective galaxy. And the nuclei of these galaxies, the supermassive black holes, form binaries that continue orbiting one another long after the galaxy merger appears to be complete. It's these remnants of galaxy merges that we would hear most strongly in the ultra-low frequency range, specifically around the nanohertz range. Yet, just like how the human ear cannot hear sounds with ultra-low frequencies, LIGO is deaf to this cosmic cacophony. If we could listen in, we would gain new insight into galaxy merges and black holes. But that's not all. One of the most exciting things about the gravitational wave background is that it is a window to the very first moments of our universe's existence. Let's quickly recap what we know about the cosmic microwave background. This microwave light is the earliest light that we can detect, because for the first 400,000 years, the universe was opaque to light. What does it mean for the universe to be opaque? Initially, the universe was far too hot for neutral matter to exist. Electrons and protons were unable to bind together and form neutral atoms simply because they had too much energy. This state of matter is called plasma, the same stuff that stars are made of. And the universe was filled with it. Light gets trapped in plasma, unable to move through space without bumping into the charged electrons and protons being continuously absorbed and emitted. But once the universe expanded and cooled down enough for the protons and electrons to coalesce into neutral hydrogen and helium atoms, it suddenly became transparent. The light was finally freed. This light was then stretched by the expansion of the universe until it redshifted into microwave light. This is why the cosmic microwave background is the earliest light of the universe. But gravitational waves are not made of light. They are made of space-time itself. Plasma is no obstacle to them. To gravitational waves, the universe has been transparent from almost the very instant of the Big Bang itself. They can penetrate past this plasma barrier and offer us a glimpse of the very first moments of the universe's creation. Because these primordial gravitational waves have been traveling for so long, even if they were originally produced with a high frequency, They would be greatly stretched by the expansion of space-time. They would be redshifted into ultra-low-frequency gravitational waves, the same kind that would come from black hole binaries. Together, these multiple sources will give us a so-called stochastic gravitational wave background existing over a range of low frequencies. How can astronomers retrieve this treasure trove of information about black holes, the Big Bang, and more? Can we build a better LIGO and detect how the Earth is bobbing up and down in these gargantuan gravitational waves? Well, LIGO works by sending two beams of light being sent along perpendicular tunnel arms. The beams are reflected by mirrors at the ends of each of those tunnels, and they return to the starting point and are compared with each other. This is so that if space-time gets distorted along one direction, the information from the other direction can be used to get a sense of how much it has changed. Unfortunately, if we were to design a new LIGO to detect these gravitational waves, we would need to have tunnel arms that are much larger than anything we could build on Earth. This is because the frequency of a wave is inversely proportional to its wavelength. Ultra-low frequency waves have an ultra-long wavelength and would require us to look at changes over a much greater distance to notice the effects of these gravitational waves. For nanohertz waves, that is one full fluctuation taking 1 billion seconds. A quick calculation. Wavelength equals speed of wave over frequency tells us that the wavelength would be around 10 or 17 desmers. For a sense of scale, the distance between the Earth and the Sun, or an astronomical unit, is 10 out of 11 mers. A light year is around 10 or 16 mers. The wavelengths we are discussing are tens of light years long. Clearly, we cannot build anything suitable for this task on Earth or even in orbit.